right. So I'm Jeff Hammond. I work for NVIDIA. I moved to the GPU communication software team, so it's Nickel and NVIDIA. Before that, I did HPC software, Fortran, and OpenMP and some other stuff. I've been in HPC now for almost 20 years, and I'm a chemist by training, and that's actually the motivation. I'm not a computer scientist. I don't care about computer science academic topics. I just solve problems. And I'm going to talk about MPI and how it solves real-world problems. The two biggest things I've done in MPI in my career are the most academically uninteresting, uncompelling things that have ever been done in the MPI space, which means they're important because they were not created by computer scientists. They were created because users wanted them. All right, so I'm going to talk about 5 things about MPI. This is not a tutorial. I will link to some tutorial content. I'll link to some stuff you should read. I will not go in detail in everything. There are papers that you can read about this. I know that not all of you care about the same thing. Some of you probably care about Fortran. Some of you don't care at all. Some of you don't write MPI code. You just deal with users that can't install it. So hopefully I'll have something for everybody. 5 topics. Hopefully at least one of these is compelling. And then hopefully that there's enough here to provoke interest that you can go off and find more. But there will be some depth on the stuff that I think is interesting. So first I'm going to talk about ABI, Application Binary Interface. This is what I think some of you care the most about, or the only thing you care about MPI lately, because this is the thing that makes package management sane again. So there's this paper we wrote for EUM'25. There's a YouTube video, I think, of the talk that I gave about it. It's an open access paper, so you don't even have to work. The archive version is stale, so read the ACM open access more. So API versus ABI. So MPI has until this year been an API standard, which means we have things like the broadcast function, which takes normal C data type arguments, and things like MPI data type and MPI com, and they are unspecified and they are opaque. They have some properties. We know they have to follow certain rules, but they are not defined. So they're defined by an implementation, and they get compiled into some binary code depending on what you do. So in OpenMPI, they have incomplete struct pointers, and in MPitch, they have ints. And these are incompatible in a binary sense. They're not the same size, and they don't have the same properties. So there's a lot of other stuff in an ABI, all the constants that are also opaque, but they're different between implementations. And then we have the shared object names and the versioning and the calling conventions and all these things. So all of this stuff, as you know, if you link against one MPI and use another, bad things happen. So the current status quo with ABIs is we have the MPitch ABI family and the OpenMPI ABI family. And there are, of course, a couple of other MPI implementations in the world, but for the vast majority of us, there are 2, and they are incompatible. And if your ISV ships a binary built with Intel MPI, you can use it with MPitch and MVPitch, and you cannot use it with OpenMPI, and vice versa. And then folks know that there's Amazon MPI, and IBM Spectrum MPI. They're based off of OpenMPI, but OpenMPI, to the best of my knowledge, doesn't make any guarantees about the compatibility, although they make some other guarantees about container launching and some things that are better maybe than MPitch. But so we have a problem here, right? You have to know what your binary was compiled with before you can actually use a program, and that's not what we like. We like apt get install blah, and then it just works everywhere because glibc is the only thing that is used by the majority of distros except for Musel, and that's a whole other thing. So there was demand for ABI compatibility in the problem that I just described with Intel MPI, actually. So even though it's the MPitch ABI initiative, it was motivated by the Intel ABI because ISVs were shipping with Intel MPI and everybody wanted to be compatible. And so they said, hey, MPitch, can you become compatible with Intel MPI, and then we'll all be downstream compatible. And they did that, and they've been successful, and it's really popular, except every once in a while somebody throws into a dangling SO dependency, which still breaks things. So we made this go away. All right, so why do this? I think you all understand, you know, EasyBuild, SPAC, apt, you all want this. You all want to stop having application-OMPI, application-MPitch, application- you know, who knows what, and have all the problems associated therewith. I know some of these folks at build tools, and you know, having to build a tool every single time for every single MPI library. Containers is the whole reason that this is happening. More efficient testing is obvious. And then third-party language support. So this is actually derived out of the working group that was focused on third-party languages like Python and Rust. And they said, actually, please, MPI Forum, stay away from our language. Do not define our binding. We do not want your help. We've already done an API that we like, that is Pythonic or Rustonic or whatever you want to say. Just give us an ABI, because we're sick and tired of having to write C glue and having to build everything twice. So, you know, the problem is obvious enough, and we're solving it. So the reasons, you know, people wanted this solved 20 years ago. The first reference I found to someone saying, so when do we get an ABI standard, was 2006. It was, I believe, the first month that the OpenMPI user list existed, and some guy said this, and they goes, basically, no. And here we are 19 years later. So the reason why we didn't do it, okay, so there are some architectural reasons that the glue that goes into the front end that would make the ABI nicer. You know, there used to be some processors like BlueJean, which is near and dear to my heart, and obviously a big deal here. BlueJean had a really dumb CPU, and so every single branch and every single 64-bit, you know, integer op in the front end would cost you just a little bit of a nanosecond, and you know, after a while you started to see it. And so, you know, people said, okay, we don't want to add any overhead and all these things. And the other thing, of course, is when I started, you know, I would compile NWChem on DEC Alpha, and IBM Power, and Itanium, and every other bloody chip with a different OS. Linux wasn't even uniform everywhere. There were all sorts of weird operating systems. And so even if we'd had an ABI standard in MPI, you wouldn't be able to do anything with it because none of your systems were compatible. And now, by and large, every single person in the world that does HPC uses Linux. And by and large, we use one of two processor architectures. And it doesn't really matter if there's more, right? Everything that we've done for ABI is beneficial to x86 and ARM, is just as beneficial to RISC-V and IBM Power and anything else. But you know, the world is simpler and different now. We all use shared libraries. Like, you know, static linking used to be like the way you did it, because shared object loading was expensive and nuked your file system. We just don't care about that anymore. All right, so I'm going to talk about the ABI design real quick. The release candidate PDF has all the details, but isn't public, but I can give it to you. I don't know why it's not on the website. Maybe just people take it too seriously. Anyways, we defined all the constants. You know, this is, you know, tedious, but you have to pick a number for everything, a number between -2 billion and +2 billion. You have to have a reason for it. So some of these, they're rules you have to follow. You know, they have to be powers of 2, or they have to be ordered, or they can be arbitrary. So I got to pick most of the constants, and then we argued about them and changed some of them, and now we have constants. The cool thing about it is the constants are by and large unique. So to the extent that you would like to help a really, really dumb user, you can. So you can take a constant that's wrong and say this constant doesn't make sense, and you could tell the user, you have passed MPI blah 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 to this argument, and that's wrong, rather than telling them the number 137 is wrong here, right? And this is potentially useful if you want to do error checking. You know, some of these magic numbers, if you've ever run through GDB, you know that like the MPitch com world is, you know, 0x8000, whatever. You know that. And so you can memorize these constants if you want to look them up in a debugger. But we have them. All right, handles. So we went with the OpenMPI solution because it's type safe. And that's really, really important to know that, you know, to have a compiler be able to tell you, sorry, you are trying to pass MPI com to MPI group. You've got these things transposed, whatever. And I've done this wrong. And, you know, people with 25 plus years of HPC programming experience who worked with me at Intel have done, you know, passed the wrong arguments. And MPitch, because of integers, didn't catch it, because an int doesn't, the compiler doesn't know what to do with an int. It just says, oh, everything's an int. And then we had to define all the predefined constants like com_world and the like. They're all in a Huffman code, which is, I learned what a Huffman code was from Wikipedia and then wrote one for this. So yeah, I got to be a real computer scientist for a day. The neat thing about this is, so MPitch has the advantage of integers is they translate trivially between C and Fortran. And OpenMPI has to have a lookup table. Now, one of the things that's cool about the way we did the constants is their compile time, because Windows requires that, not that I care. They're less than 1024, which means they fit into the 0 page, so they'll never conflict with a user-defined pointer handle. And they can be converted to and from Fortran trivially. So if you have com_world, you can just go, bang, it's less than 1024 cast and go, right? So you don't have to look up on the critical path anything for the predefined. The only time the lookup is going to hurt at all is when you you do a message rate test and you do 1 million requests and then you can back convert, you know, whatever, thousands, however many you do. And that's not a real use case. It's just a benchmark, just like Lint. So anyways, this is done. This is fun. This is the hardest part. I did not think that this was going to be the majority of the time I spent on the ABI, was defining which integer types were these. So this is what they are. Basically, we had to figure out that, one, all file systems are and have been 64-bit for about 20 years, and they will be 64-bit for at least 20 years. I actually went through and did the math. If you want to do a 128-bit file in MPI, you will need to spend $20 million on hard drives to make one file. And so obviously, none of us are going to do that. And you know, if you want to do sparse, I don't care. Like, that's having 128-bit offsets just so you can have a really small file with really weird sparse indexing doesn't matter. We had to kill MPI fint. And the reason is, this is the most horrible thing in the world, because Fortran has the most horrible feature in the world, which you can change the size of an integer and a real and other data types with compiler arguments. And many of you may know this, because if you're a quantum chemist, you compile all the quantum chemistry codes with -I8. It's absolutely an abomination. It creates a totally different ABI, and the possible variations supported creates a very large multitude of ABIs that we just said, no, we're just not. So we killed fint, and we're going to replace it with a trivially equivalent to from int. It's just the thing that everybody is doing today, except it's got a fixed C type. And this is fine. Everything will work. I can go into the details later. So we're good to go on everything until somebody wants a 128-bit ABI, and they can add it. I actually spent a non-trivial amount of time looking at Cherry just to say, are we doing anything that's going to be tragically regretted when we get there? And the answer is no. So let's see. So this, some of you may hear a lot about this. So obviously, we're not going to break existing code. So we're still going to have MPI.h. It's not going to be MPI_ABI.h. That would be really bad. No one would use the ABI if we did this. So it'll probably be in a different folder. And the MPI SO, shared object, will have, you know, whatever the conventions are for your platform. Obviously, you know what these are in Linux and Mac. So the reason it's got the _ABI is just to make it really clear. So, you know, if you do dumb stuff with a LD library path, you'll not find the wrong one. We do ship a stub implementation, and this is actually, I think, this is actually going to be cool, right? So I have friends, NVIDIA, who are trying to build containers, build containerized applications to run on our supercomputer, and they do not want to have the MPI library that they're going to use on the supercomputer on their local system just to build a container. So we're going to ship a stubs thing that's an SO that defines the ABI exactly, and every single symbol maps to a board. And so what you do is you take this thing and it builds in, you know, 2 microseconds, and then you compile against it and you link against it, and then you send that thing off to the containerized cloud, and then you link again, you know, at dynamically load the SO that you actually want, and it works because that's the whole point of an ABI. So we'll now have a stub that'll hopefully save time. The other thing is this keeps people honest. If you build against the stubs SO, it should work. And if it doesn't work, when you go and hot swap in your implementation, then something is wrong with that implementation's implementation of the ABI. You should not have a problem if it's a correct implementation. Okay, so the ABI is versioned. It'll start with 1.0. It'll go up, minor version, every single time we do a release of the standard, obviously, because we discussed this. Are we ever going to do a release of the MPI standard that adds nothing? And the answer is we don't think so. So we'll always add at least one symbol or something, and so we'll have a new ABI every minor. And then, you know, if and I will probably retire and live in the woods if this ever happens, because we really don't want to break backwards compatibility. But if we ever screw something up and we have to change the ABI, obviously we'll increment the major version. Hopefully that'll happen after I'm retired, so I don't have to go live in the woods in shame. So I'm going to talk about Fortran. ABI in a platform from an MPI perspective is defined by, you know, the OS and the C compiler, and we sort of, I basically swept almost everything under the rug by saying that the ABI, the calling conventions, all that business is as if compiled by the system C compiler. Because we all know we have a system C compiler that defines the ABI, and if you don't use that tool chain or one compatible with it, you're not really able to do the stuff you would expect to do with shared objects. Like if you go on, you know, if you build something with Musil and then you go and try to run it with glibc, bad things are going to happen. Like you have to be building with the standard tool chain for your operating system. There's also the file system, the offset is weakly part of the ABI to some extent, although we said 64-bit and done. And then as previously mentioned, there's this awful thing with the Fortran compiler where integer and real are now dynamic properties because users can switch their properties, and not just two different options. Intel, I think, has the option to make integer 2, 4, 8, and maybe even 16 bytes. It's really wild. I mean, the 16 or the 2 I understand because that's like backwards compatible to 16-bit something from, you know, the land before time. But the thing that's terrible about this is, in addition to MPI FINT, these are visible in the C ABI because of MPI type size. So in PETSI, for example, MPI type size might call MPI real because they're going to do everything in C, but they're going to hand it over to a Fortran user. So C has to know what MPI real is. So now we spent a long time on this of how do we separate this? How do we make it so that the C implementation of MPI does not need to know about properties of Fortran, and not just the properties of Fortran in general, the properties of the Fortran object code that users compiled. And this is really nasty. And so we spent a lot of time on this, and the solution is not pretty, but it's, I'm blaming Fortran. And I've been on WG5 for the last 4 years or whatever, so I understand why the problem is the way it is. I don't like it, but I don't have a time machine, so it is the way it is. And the other things in the Fortran compiler that don't matter as much to see, like string passing, CFI, descriptor, those ABIs are visible at the compiler level, but don't really show up in C. And then the module format. And the reason this matters is at some point you're going to ask, oh, do I have an MPI Fortran ABI? The answer is no, because as best I can tell, I haven't proven false, so I have to assume it's true. The source code layout of a Fortran module is part of the name mangling. So if I have MPICH does, the MPI module is based on 4 submodules, not proper submodules, but include modules that are part of it. And that shows up in the name mangling that you look at when you see the symbols. So what that means is we cannot specify an MPI Fortran ABI fully without specifying the source code. And that may happen someday, and I'll tell you that it's likely going to happen at the same time that we deprecate Fortran from the MPI standard and say it's a third-party language, which would be really good, but also for people that don't understand, might they be like, oh my God, Fortran is dead, you know, burn my punch cards, and they would rage tweet about it, or rage whatever the social media beast guy, whatever people do. And they wouldn't understand what it means. So, you know, I'm in the process of prototyping this, building a third-party MPI Fortran support to see if this is possible and how well it works. But, you know, for the meantime, what we have is a C ABI that knows something about Fortran we don't have a Fortran ABI, and that's unfortunate, but we can't solve everything. All right, so we did this stuff basically. If you have an MPI implementation that includes Fortran support already, like most of the implementations when they're compiled with Fortran support, you don't care. But if you want to build them separately, which I'm working on, there's basically some API functions that allow you to tell the C library about Fortran. So you can basically say the size of MPI real is 4 bytes. The size of MPI integer is 4 bytes. And the binary layout of MPI logical is this, because by the way, Fortran logical true and false are not 0 and 1 like C. They're probably 0 and either all ones or 1. And so there's all sorts of fun stuff. But we did solve this. It's gross, and hopefully none of you will ever need to know about it, but it's there. So we've had so many votes. We have like 50 no votes, which is our way of saying, like, you know, if somebody really hates it, they can veto it. I'm hoping that doesn't happen. But probably virtual meeting right before ISC, we will finally be done with this whole darn thing, and it'll go public. There's like 1 or 2 controversial no votes that, you know, and if we lose them. But we should be done by ISC. Some common questions. So launchers are not really standardized, and they don't need to be. So the first part is in an HPC context, most people use Slurm or something like Slurm, and it doesn't matter if it's Slurm or not. But all the common launchers are recognized by MPI, meaning you don't have to MPI run with the thing that your app was compiled with. You just srun, and srun will set a bunch of environment variables, and then all the MPI programs, when they're spawned by the spawner, will go look and say, oh, I know how many processes and the topology, everything else. So that's all fine. The other thing you can do is you can make sort of a magical MPI run that will basically set the right LD, you know, path so that they'll match if you want, as a convenience. So wrapper scripts, they're not standard, but everybody knows that they're pseudo-standard, and the implementations agree, and we'll figure that out. It should be fine. And, you know, nobody's going to throw away their current ABI, so if you've got a bunch of binaries, they're going to work. You know, it's going to be years before anybody goes off and abandons their current ABI for the standard one. Everybody, I think, will ship both. MPitch today ships, you basically build, you say, I want the ABI standard, or I want the MPitch ABI. You can get one or the other. OpenMPI is not implementing the ABI yet, although I've heard they'll do it this summer, and then we'll find out. But most likely, you know, sysadmins will have to decide what they're going to do. Hopefully the Linux package manager people get on board with the ABI, and then we can sort of drive adoption that way. All right, so that's ABI. If you want to ask questions, I'll be here all day. Large count support. So this is one of the, so I did this. It's the reason why we can't print the book anymore, because it added like 150 pages, because we added, you know, 2 of every symbol. The reason it's not interesting at all, but I'm putting it in here because there's been interesting progress on this. You can read a paper about it if you want. So support for large count. So basically, count is, you know, the number of elements in a message, and it's been an int. And you know that an int is 2 billion and change at most. And if you give it 3 billion, terrible things happen. And it's not MPI's fault. It's your fault. You're using C incorrectly. So don't get mad at MPI that they do bad things. Get mad at C that they didn't switch to size T when the C Linux community did whatever. And there's a reason they didn't, and I know why, and life goes on. But so now we have a second symbol. We have an _C symbol and a count argument, and count is big. You know, it's at least 64 bits. So you don't have enough memory to overflow this. So we're good to go. And you have 2 symbols, and we tried to make this not, you not have to know which symbol you were calling with C11 generic, and it turns out you can't, it's too hard. C11 generic combined with multiple count arguments, especially count pointers, combined with the abominations of the C implicit integer type promotion rules, is absolutely dynamite, and not in the good way, in like the Minecraft blow your base part way. And so we just can't do it. And of course, you know, if we had C++, we could also try to solve it a C++ way, but we don't have C++. And so if you want to make this happen, you can always, you know, wrap MPI and do it. On the other hand, Fortran is awesome and has polymorphism that makes sense because they don't have integer promotion rules. And if you give the wrong size integer argument, Fortran says, new phone, who dis? Says, I don't know what symbol you're talking about, you're giving me the bad stuff. So you can distinguish unambiguously between an integer and a count integer. And so we have the underscore C symbol if you really want it, but you don't have to do it. Module polymorphism solves this problem. You're good to go. As long as you're consistent. If you give it one integer and one count thing, it doesn't recognize that at all. You have to explicitly cast. So this is in the MPI F08 module because that's where we have all the goodies and all the polymorphism. We do not have large count support in MPI module or mpif.h. I'll get back to this in just a second. If you would like to use new and awesome things in MPI, you need to stop using mpif.h, and you should probably stop using the MPI module. mpif.h is deprecated and terrible, absolutely terrible. MPI.mod is only slightly less terrible, not yet deprecated, but hopefully will be soon. So the reason I mention this, MPICH drops every single feature, or releases every single feature of the MPI standard on the day that the vote happens. They actually have it all in a branch, and literally the vote happens, and like 3 minutes later they hit rebase and squash rebase merge, and then they push it. And MPICH has support for large count on November 2020. And I didn't check GitHub, and they haven't woken up in the US, but my understanding was the large count support in OpenMPI was supposed to be merged on Tuesday, meaning today, or yesterday, whatever day it is. I don't know, but it should be very, very soon. So this has been something that has been long requested from some folks. So OpenMPI will have large count support very, very soon, and now you'll all be able to use it, and that's awesome. That's part of the reason I mentioned this. OpenMPI has this. Okay, so now I'm going to talk about Fortran. I gave a talk about this. It's from Pask. They recorded it, and it's not public, but it's my video. I put it in my Google Drive so you can check it out there, and hopefully they'll let me post it on YouTube or something so I don't have to give the long version of the talk ever again. But I'll give you the short version here, and you can get details from that if you want. So I've alluded to a lot of this. So we have in MPI language support for C, and of course all the languages that aren't Fortran use C. So Python's MPI for Pi sits on top of C, Julia, Rust, etc. And I looked actually, I think every language that mainstream, even esoteric language that I looked up when I did this a few years ago, except for COBOL supports MPI wrappers. I don't think COBOL needs MPI wrappers. We deleted the MPI C++ bindings in the 3.0 because they were not good enough to bother. Some people like them. Most people hate them because they're not modern C++. And if you know anything about modern C++, absolutely nothing except for code written by one person is good enough for that person when it comes to definition. So everybody has their own C++ wrapper, and theirs is better than everyone else's according to them. And so there's nothing we could do to help these people except for giving them the C API. So we do. mpif.h commonly and incorrectly called F77 bindings, because if you don't know, MPI init has 8 characters symbols in it, and that is not compliant with F77, which only mandated 6, which is why Blas and Lop look the way they do. If you've ever wondered why those symbols are so inscrutable. So mpif.h is terrible. MPI mod is basically the mpif.h API, but in a module, which is slightly better. Commonly incorrectly called the F90 bindings. They're not compatible with F90 either. And then there's MPI F08, which is the good stuff. I'm going to talk about this. So first thing, we deprecated mpif.h. It's terrible. You should really not use it. There was a section in the MPI standard devoted to telling people how terrible it was and why they should not use it. And everyone's like, I'm just going to ignore you and keep using it. And so we deprecated it, and they're still using it. OpenMPI is going to implement a deprecation warning, and hopefully that'll scare some of those people enough And eventually, you know, sometime before I go retire and live in a cabin in the woods, maybe people will stop using MPIF.8, but it's really bad. So I'm going to tell you why you should use MPI F08, and why it's okay to use it, maybe because implementations are better than they have been. So first thing is, so when you do MPI broadcast, right, in C you have a void star, and C is cool with this. They're like, you can give me absolutely anything as a void, any pointer you want as a void star, it's bytes, and I'm going to ship it. Fortran, this is not okay. But the good news is, for 30 years or more, Fortran compilers have been like, yeah, I don't care. I don't do type checking. I just take whatever you want. If you want to give me a real, you want to give me an int, I will treat it like C. Well, it turns out C compiler, or Fortran compilers like GCC, are starting to get really, really angry about this and are throwing lots and lots of warnings. And they're right. And, you know, warnings scare some users, sometimes for good reason. And so, you know, the fact that we basically abuse the Fortran type system and use these weird extensions that basically said, please, I know you were going to try to type check for me, but I know what I'm doing. Let's turn off all type checking on this argument. You know, we basically make MPI work because of this. The other thing is you can't use Fortran array properties, including subarrays. So subarrays will work or not work in very nuanced implementation-specific behavior depending on how your Fortran and your MPI library work together. Sometimes bad things will happen, sometimes they won't. Blocking probably works some of the time, and then non-blocking almost certainly won't work. But it might not work 100% of the time, in which case you might think that it works and then it won't. Bad things. All this is terrible, right? This is not what we want. Okay. The other thing, so just kind of like the MPI ABI, you know, having all the handles be integers turns off type checking. So, you know, if you're really smart and you never make any programming errors or use an IDE that's got all sorts of AI in it, always checks everything for you and it knows about this, fine. But type checking in general is good, and we don't have this. So again, another reason not to use old school Fortran. So MPI new Fortran, MPI F08. So we have type star dimension. This is a proper void star equivalent in Fortran. This does two things. One, it's actually using the Fortran type system correctly and telling Fortran, I can give you anything I want here and it's okay. And then second, this actually triggers the magical back-end support to convert to C and have an array descriptor and do non-contiguous subarrays and do all sorts of beautiful stuff with that that some MPI libraries do, and I'll get back to. Second, F08 is type safe with respect to the handles. So there's a type, so you cannot mix and match types incorrectly. The good news, it's also backwards compatible because that type is nothing more than, you know, it's a Fortran struct that includes only the integer. So if you actually pass it to old Fortran, for example, it'll work because it'll interpret, it'll get interpreted as the thing it contains. But so it has good properties of backwards compatibility and type safety. So we also get, you know, large count support magically for free, and that I already talked about. Now this is where the, you know, landmines start to come into play. So Fortran has something called asynchronous. It's kind of like volatile, but it's slightly better in that it doesn't inhibit all compiler optimizations, I think. But the reason this is important is, so this is iReceive. This is non-blocking receive. And if you know anything about non-blocking receive, you call iReceive and you give it a buffer. And then it returns and nothing happens. And then magically, somewhere in the bowels of your computer, sometime between the time you call iReceive and the time you call wait or test or whatever you do, buff gets written by the network. Well, what happens if your compiler, and most compilers, I don't know any modern Fortran compiler that does this, but they're allowed to do this. They could say, well, hey, you're done with buff. You passed it to iReceive and now you're done. I'm going to use the memory associated with buff as scratch space and fill it with junk just for fun between the time you call iReceive and the time you call wait. That's allowed, right? Because Fortran says, you're done. You passed it. This is just free space sitting around. Why don't I scrub that? or do whatever with it. Asynchronous says, Fortran, you can't do that, okay? And the good news is they haven't, because a lot of things, including iReceive, would not work if they actually did weird stuff, but this is the right way to define the interface. The other thing that goes on here is if you pass a subarray, I'm going to show you what happens where you need the async in conjunction with some other stuff if you pass a subarray. So most people don't pass subarrays to non-blocking MPI, but if you do, you are playing with fire. There are safe ways to do this, and it will work if you do it right, but almost certainly people who do this are not careful enough. So the good news is if you use subarrays with broadcast, blocking calls like broadcast, for example, everything works fine, because the compiler will either make a temporary or it won't. But if it makes a temporary, the lifetime of that temporary will be the entire duration of MPI bcast or all reduce or send or whatever it is. And so it's fine, because Fortran will make a temporary, call C and the MPI stack, and then the network will do its thing, and then it'll come back out, and when it exits from the C part of the networking stack, it will free the temporary and go back and everything's good. But if you do iReceive, right, iReceive returns, and the temporary that was created, poof, goes away because you're done. And then, you know, maybe sometime before, but as late as when MPI wait is called, the network goes, cool, that address of temp that you gave me, I'm going to RDMA right to it right now, except it's gone. Boom, right? So this is bad. But the good news is you should know that this is going to happen to you, but you probably don't. So because you don't check. But if you're going to do subarrays, you need to check subarray supported is true and async protects non-blocking. So together you check for these things, then you'll know that async does what it's supposed to do, and that the subarrays are actually implemented in the way that's going to work, and I'll show you what that looks like. So this is not a reason to tell people not to pass subarrays to MPI. It's just that they darn well better check both of those module attributes, or whatever, module globals, whatever they're called. Those things, check them to make sure that what they're doing is safe. You know, you just check them after init if you want, because, you know, and then just throw an error and say, this program is not going to run with this implementation. So MPitch supports the interesting, most likely to be used subset of this, and OpenMPI does not. So OpenMPI will work for blocking stuff just fine. The Fortran compiler makes a temporary and life goes on. But if you do iReceive with OpenMPI and subarrays, bad things may happen. So here's how you make this work. And this is what MPitch does partially. I have an implementation in something called VAPA, which is the Finnish word for free range Fortran MPI module, where I do absolutely everything the standard says is allowed, and it allows some absolutely absurd stuff but that no one will ever do. But I supported it just to be academic. But MPitch supports the only reasonable use case. But what happens is inside of Fortran, when you pass, you know, type star dimension ... it turns it into a CFI C descriptor for the array. And inside of the MPI library, it can take that descriptor and turn it into an MPI data type, and then do iReceive, and everything works perfectly. You don't have to use a data type, but that's the easiest way to do this. The fun thing is when you combine a subarray with a user-defined data type that's non-contiguous, and we did not say you couldn't do that. You shouldn't do that, to be clear. No one should ever do that. Like, if you want to do non-contiguous subarrays, be happy. That's non-contiguous enough. Don't do doubly non-contiguous MPI, because what happens is, what I do to implement this, and you can see the code, it's truly disgusting. You basically have to map the non-contiguous subarray to an IO vec, and then do, like, you know, I don't even know what the mathematical thing is, but basically, you know, the set union of the non-contiguous map, memory map of the Fortran thing with the non-contiguous memory map, which is relative now, into that. And I did make it work. MPitch will support basically Cartesian things. And so if you do Cartesian subarray's life is good and otherwise bad things happen, or it'll just say no. All right, so implementation status. So one of the things we needed for this to work everywhere is, and it's CFI, not CFD, it's a Freudian slip because of HPC. NVHPC Fortran was the last major compiler to support this feature, and we do now. I was part of that when I was in that team. So that has been implemented, and so we should be good to go everywhere. The compiler also needs to support all the assumed rank, assumed type stuff, which should be there as far as I know. And then the implementation has to use the CFI C descriptor, and MPICH does this and OpenMPI doesn't. They're both valid as long as they correctly report whether or not they do it. And the other thing that some of you may hate, and I've been complaints about this online, you know, MPI, the MPI part of, or the MPI library is like 99% C code. And it takes, you know, like 3 to 10 minutes to compile based on how fast your file system. It's slightly easier to compile than LLVM, but not so much. But, you know, you have to compile it for every single Fortran compiler. And no one has separated this out. It's not a problem that anybody cares about, and it's a build system. There's no glory in this. So, you know, you have to build this separately every time. So if you have Intel and GCC and Cray and everybody, you know, Flang, you got 4 plus compilers. And people don't like this. So that hopefully the thing that we'll be able to do in the future, which I'm working on, MPICH is also looking at it, is separating Fortran and C enough so that these things are either fully or partially separable to the point where they could be built separately and they interact with a well-defined interface, meaning the C ABI. And actually, there's some folks. I have some real users of APA now that basically they want to use MPI F08, and they just want it to be simple and easy and separate it from their MPI implementation itself. And so this is working now. People are actually using this. It's an incomplete project, but you can see GitHub. All right. So I'm going to talk about RMA about 15 minutes. Hopefully I'll get there. RMA is not like send, receive, and collective. So almost everybody, all the physicists, all the chemists, even some of the biologists can do send, receive, MPI collectives. Doesn't take much. You teach them in a day. People go off. They write their code, CFD, Monte Carlo, whatever. Life goes on. One-sided is by far the hardest thing to use. Even the people who are in the room when it was written still forget what's in it and still have to refer to it like I did last night. But there is merit to it, and I'm going to explain why it's useful and hopefully how to use it. And so I'm going to turn this into a blog, hopefully, so that people will stop asking me to explain RMA to them because it's inscrutable. So send receive is nice in that it encapsulates a couple of different things into one operation, and that makes it easy to reason about. The bad news is it encapsulates a couple of different things into one operation. It encapsulates an ordering semantic, a synchronization semantic, and a data movement semantic. So you have to match in order, which often requires either, I mean, if you do eager protocol, it's a copy, and if it's a rendezvous protocol, it's a handshake, and then you move the data. RMA says, I'm just moving the data, and I can move it ordered or unordered, and all the synchronization is separate, which makes it harder to program because you have to manage all the synchronization. But from a performance perspective, it's nice because you have total control. So this is useful in unstructured apps. So NWChem is probably the most widely used one-sided code in the world. And it does basically random access reads to distributed memory, these big tensors that are hashed across distributed memory, and they're accessed in a dynamic fashion because there's a dynamic load balancer. And so you can't post sends and receives because you never know who's going to be fetching from who. And you could do this with active message-like stuff and then do that over send receive, but the semantic is one-sided. And there are other algorithms. You know, there's an algorithm where you basically do sorting, where you sort of sort and then you look at the things and you scatter to everybody. But you sorted your local array and then you scattered it. People who are receiving don't know that they're going to be receiving from you because they don't know what was in your local data and how many buckets of you know, sorted keys and values you have. And so you know, that's another situation with sort of a write-oriented unstructured workload. There are also, in theory, better matches for hardware. So RDMA read-write should map to put get in theory. They don't always. Implementation detail. RDMA atomics should, but don't always, map directly to hardware atomics or MPI atomics. And the good news is, you know, all the registered memory stuff that shows up in like IB and other networks, that is all encapsulated in window allocation. So you separate that. So you don't have to do these registration caches and deal with all the overhead of figuring out what the M keys are if your network requires that kind of a thing. So one-sided is potentially good, but it's kind of chainsaw juggling. So this is old, but BlueGeneQ is a beautiful machine and had a beautiful network, and so it's really nice to show this. So the things that aren't MPI IRSend are PAMI, the low-level thing, and the RPut and RGet are RDMA. And what you can see here is if you look at all right, sorry. No, it's fine. I'll just virtually point with really long invisible arms. So IRSend is down there, and like BlueGene had about as good a send receive performance as any HPC system in its time, and yet if you look, there's like at least a 2x bandwidth gap for medium-sized messages relative to RDMA. And the reason is there was protocol overhead, that it had to go over there and it had to handshake, had to do an active message callback, and then the data would move. Whereas in, you know, the low-level messaging layer, you could just say, go. You already know where it is, you know the address, and you just shoot it straight at the network, and it goes straight into memory with nothing else involved. And so this is one of many examples where one-sided is better than two-sided. So ecosystem, this is an extremely biased thing, meaning I have either written or been a consultant on every one of these projects. There are other stuff out there, but I'm going to talk about what I know. So both of the major portable implementations of CoRays, CoRay Fortran, use MPI RMA. Intel MPI, or Intel Fortran was using Intel MPI for, and they were using RMA, they were using it poorly when I joined Intel. It was very slow. I called up the compiler team and we talked about what they were doing, and I explained to them how RMA worked, and they were able to go in and make it a lot better, and it's at least competitive now with other things. Open CoRays project, which is the backend for GCC Fortran, it has other backends, but I believe MPI is the only one that actually gets used, and that works pretty well as well. Alessandro Fonferio and Damien Roussan have done a lot of work there, and they like it's a very nice effort. Other than buying a Cray machine, it's about as good. NWChem is something I've worked on my entire scientific career, and one of the things that happened when I was young is, you know, basically every time we get a new supercomputer, we'd have to wait a year for NWChem to run on it, because somebody would have to write a new networking port of ARMC to Quadrix or Verbs or BlueGene 1, 2, 3, and then Cray, and then a new Cray networking stack. And then they had to re-implement all the flow control for the Cray thing. Every time they got more than 10,000 more nodes, they had to redo the flow control because, you know, again, all this stuff that MPI already solved or should solve had to be re-implemented. And so my colleague, Jim Dinan, actually colleague at every one of my jobs, and current teammate, wrote the first version of ARM's MPI before MPI 3 existed, and then I took it over and made it MPI 3. And I've never published it because it turns out running NWChem is sufficient motivation for me to keep maintaining it. And then we wrote an OpenSHMEM over MPI. It does have some users, interesting enough, because it's the most portable, easy to use OpenSHMEM out there. It's not the fastest per se, but it turns out it just works because it's MPI. And one of the things that's useful about this project, if you want to go look it up, is not that it's a good implementation of OpenSHMEM, it's that it's a tutorial on how to use MPI RMA. So if you understand SHMEM, which is a relatively simple one-sided model, you could basically look up the implementation code in that project and say, well, this is how you implement blocking put, this is how you implement atomic, etc. So in total, we have the only standardized PCAST language, the only one-side, or the original one-sided library, EUM'25, and the most widely used one-sided application, all demonstrated on MPI RMA. So I think this is a pretty good, sufficient demonstration that MPI 3 RMA works. And I've spent the last 13 years breaking all the implementations and making them better. But I'll talk about that they're better now. So I'm going to have to go a little bit quicker. This is up as text, and hopefully it's a tutorial you can follow along later. So the bad news about RMA, you have 4 window types, 4 ways to allocate distributed memory, and you have 3 or 4 synchronization motifs, depending on how you want to look at it. And that's 16-way complexity before you even move any data. And you say, oh my goodness, this is a whole lot of complexity. I'm now very scared. How do I choose these things? Maybe I should just go back to using send receive. And that is a reasonable perspective. The thing that you should do when you look at RMA is you should figure out what you actually need to use and don't look at anything else. Horse blinders, right? Just like you've been using MPI, 850 pages of MPI, and most of you call 12 functions, right? None of you look at the I/O chapter. It's okay. You don't look at the context chapter. You don't use the topology aware stuff. That's okay. Same thing with RMA. Just look at what you need. Unfortunately, it's not super easy to read, but eventually you figure it out, and then you just forget about the rest. So I'm going to tell you what you should not look at. So choosing window type. So we have this thing WinCreateDynamic, which you must use if you want to do multiple buffers attached asynchronously. If you're not doing that, you don't need this. Don't look at this function. You need to be able to attach a user buffer to the window rather than letting MPI allocate the buffer for you and then tell you where it was. If you don't need to attach a user buffer, don't use WinCreate. If you need to know it's in shared memory, use WinAllocateShared. Otherwise, if all else fails, and by and large, please use WinAllocate. WinAllocate gives the best performance across the board. It's got all the features. You can even get shared memory out of it now. We fixed that. And the performance will go up. So unless you have a good reason not to, use WinAllocate. Full stop. That makes that problem easy. Second, synchronization. So, are you a weirdo? Do you not want to do send receive, but you want to do send receive with RMA in a really convoluted fashion? If you are weird, you can use post start complete wait and gamble on whether or not the performance will be any good. Or you can just not use post start complete wait, continue using send receive, or do something else. Second, are you weird and do you not want to use all-to-all V to do an unstructured collective? If you are weird and also want to gamble on performance, fine, you can use fence synchronization. Otherwise, don't use it. There are no good reasons to use post-start complete wait and fence at this point. I'm not aware of any optimization, and the workload arguments for using them are negligible, and the performance gamble nukes any of the potential merits of using those features. And you can do it all with passive target, which I'm going to tell you. So one thing is a sort of special carve out. If all you're doing is calling MPI WinAllocateShared because you're afraid of calling POSIX SHMEM allocation yourself because it might not work correctly on Mac all the time because, Steve Jobs, you can use MPI WinAllocateShared and then just pretend that that's POSIX shared memory, forget all about the MPI standard, and then go do whatever you do with atomics, mutaces, and whatever, and you could do that. But that's not really RMA, so forget I said it. So by and large, unless you are weird or have very, very special requirements, use passive target. Now, passive target isn't simple, so I have to have a second slide on how to use passive target. So, do you want transactional semantics that are called lock, but do not involve a lock in any way? You can use lock exclusive. I don't know why. I know of no use case for this, and every use case that's ever been suggested is an abuse of what this thing actually does and assumes that it does things that it doesn't do. So don't use that. If you want locks, implement locks with atomics. You can do an MCS lock, you do a spin lock, you can do all the locks you want with atomics in MPI. But lock exclusive is not a lock. If your communication is limited to a small set of processes, and you don't use MPI mode no check, MPI lock might be more efficient. Okay? I've looked at the source code. Lock all with mode no check is basically a no-op. The only thing lock all does, if you don't say no check, it sends a message to everybody telling them that they're now locked with a shared lock so that they can maybe throw an error if you do a bad thing. But if you're smart and you use the rules of intelligent RMA programming and you only use passive target and you only use win lock all, you won't have a conflicting synchronization motif to error detect in the first place, and therefore you can use mode no check. So, summary. Just use win allocate, just use win lock all with mode no check. And what you should do is you should think about the lock all as being part of allocation. So when you call win lock or win allocate, just call lock all immediately. Now you are in a passive target epoch, and then right before you call win free, call unlock all. And in between, use RMA and flush. And this will behave like every other RMA one-sided model like SHMEM and co-arrays and everything else that exists, and you can have sensible code and reason about it in a normal way, like PGAS. So if you want to write blocking put, you just call put win flush local, and that says put and the buffer's ready. So flush local just says I'm done here, the buffer is yours. It doesn't say anything. It says I could have put it in a temporary queue. It could be in the network. Who knows where it is, but it's not there yet. It's just not here. And if you want to quiesce the network, like SHMEM barrier, SHMEM quiet type thing, or SHMEM barrier is more correct, you just flush all without the local, says everybody's pushed everything all the way through, and then you can call barrier and everybody knows that everybody has pushed everything all the way through, and now we're done. So in a lot of PGAS models, what you have is basically dump stuff in, spam the network, and then quiesce. Spam the network, quiesce. Global arrays does this, SHMEM does this. This is how you implement them. This is not complicated. And if you want to learn more, you can look at ARMC MPI and you look at OSH MPI and see this is basically what they're doing. It's a relatively simple semantic. And it's simple because I deleted all knowledge of PSCW and fence from my brain before I started writing those because I knew they were bad. All right, so some results. This is really old, but still useful because nothing really has changed. So NWChem running with a benchmark that's used for scalable stuff in this paper, also with an app that used ARMC MPI on Tianhe 2 back in the day, because that was the only way to get it to work. So the first one is a top figure, which happened before, so in 2014. And this was compared against the RMC provided by somebody at Cray using the low-level networking layer, and RMC MPI with asynchronous progress help from something called Casper. You read more about it online, was faster. And then PNNL did some work on RMC and did some work with using MPI and doing asynchronous progress in a different way with send receive, but active message style, and they got to parity. But the nice thing is zero code changes were required, zero network specialization other than working around Cray MPI bugs was required to get the top result, no development work, no non-portable code, anything. And this is basically the story of ARMC MPI over and over and over again, is every time something that's harder to implement or potentially faster doesn't work, either because it doesn't run at all because the machine doesn't support it, or because it, seg faults or whatever because it overflows network buffers, ARMC MPI comes in and just works. And so sometimes it's fast, sometimes it's not, but it works, and that's nice. There's this quote, I love this quote, John Oosterhout, the guy who invented TCL, says, the greatest performance improvement is when a code goes from a non-working to a working state. Like, I know we're all HPC people, but we're still all scientists. Like, the code working is actually really an important part of the performance curve. And so I like to say that the Oosterhout performance of ARMC MPI is fantastic. Omdahl, Gustafson, that's debatable. Oosterhout curve is amazing. Yeah. Okay. So I'm almost done anyways. So this is just my friends at NVIDIA did some fantastic work on OpenMPI 5 to make it way better for RMA. and then you can read the details in the footer. Basically, tail latency matters, and so the code goes way faster, even though the individual ops on average don't go faster. It's that the tail latency went way down, orders of magnitude, because they implemented everything using RDMA, and they did it in a neat way, fixed all the bugs, and it works beautifully. And I've been waiting a really long time. There's all sorts of stuff on the internet about me being super mad at the OpenMPI team for the last 15 years about RMA, and I am no longer mad at them. They've done a great job, and this works great. So RMA is hard, and everyone involved feels bad about this, and there's nothing we can do because backwards compatibility is a heavy burden to bear. It's been used a lot of places. It's been implemented everywhere. It works pretty well almost everywhere, and there are ways to get asynchronous progress if you need help with that. This is a reading list if you want to know more. Some of these papers are really, the one Torsten wrote is incredibly complicated, brilliant stuff. I don't understand it. If you're not smart enough to understand a Torsten paper, you can read the paper that I wrote, which is extremely unimpressive, extremely straightforward for small-minded chemists to understand how one-sided works. It shows how you map SHMEM to MPI, and that's pretty much all you need to know to understand how MPI RMA works anyways if you're just looking for a one-sided library. Torsten has a great tutorial on this stuff. You can read some code. So I should stop now. So I'm not going to talk about GPUs, sadly, but Okay, so let me briefly talk about MPI and GPUs, and then you can talk to me the rest of the day. So the first thing about why this is hard is when we say MPI and GPUs, do we mean a CUDA GPU or do we mean an OpenCL GPU? And I don't mean just the API. I mean, does it have forward progress? Does it have unified memory? All of these things matter a great deal when we talk about doing MPI. Forward progress is a big part of MPI that's not really documented, but if you don't have forward progress in your threads, you don't really have the ability to do all of MPI. Second, a bunch of things that are in MPI are bad on GPUs. So blocking, synchronization, and ordering are generally GPU anti-patterns. It's not that they don't work, it's just that they're really, really bad for performance. We don't want you to do those things. Blocking an entire GPU in a blocking wait call is a bad idea. So it turns out RMA is a really good model for GPUs. We haven't done the work for it yet, but we have NVShmem, which you can look at as an example of how this is supposed to work, and then hopefully we'll get there. And there's a bunch of stuff related to NUMA. GPUs are kind of like NUMA now, thankfully, than the way they were in the old days. But MPI support for NUMA doesn't like work on GPUs the way it works on a two-socket system where you have a process here and a process there. Because you don't have a process on a GPU. You have a process on a host associated with a GPU, and that doesn't solve the problem. So I am extremely biased about this because I am in the Nickel team. So Nickel is MPI for GPUs. So if you want MPI for GPUs, just use Nickel. So yes, it's not portable. There are some other CCLs. Michael Clem was here yesterday. He may have talked about another CCL. There are other CCLs in the world. The important thing is your CCL needs to know about your GPU model because it has to have the right semantics. You can't just take Nickel literally and make it run on a thing that isn't a CUDA GPU because you won't necessarily have all the hardware features and all the semantic support that Nickel's going to rely on. You can maybe do a subset and life goes on. But the key part of Nickel is there's stream semantics for everything. Hopefully that'll get into MPI 6. Nickel only implements things that are a good idea on GPUs. And this is something Nickel can do because it's not MPI. It doesn't have to be backwards compatible. It can just say, you shouldn't do that so it doesn't exist. And then Nickel programmers can only do the right thing. And that's good for performance, it's good for everybody, but it would make the MPI standard not make sense. Hopefully someday we'll get some other stuff. I'm working on the things that will hopefully lead to MPI 6 catching up to Nickel in some way. Hopefully we'll get there, but until then, just use Nickel. Thanks.
I have a bit of a question about the ABI standard. So what happens to the extensions like the MPI X stuff in various?
Yeah. So nothing says that implementation can't add that. It's just not in the ABI. If you use an extension, obviously you've got to get it from whoever provides that extension. So that will become, that'll be, is it a violation to ship that in the SO? That's a good question. I'm not going to say it is, but if you want to be clean, you should link against the stubs SO. And then if you want to turn that on dynamically, like I would recommend for hygiene, if you're going to use an extension, do it with DL open and DL sim. Like say, do I have this symbol? If I have MPI X magic, then use it, but don't hard code it into your application and then have a link time failure when you switch implementations.
Not really a question, just 2 short remarks in the interest of time. I think this slide is a good idea to invite you again next year at the EasyBuild user meeting. It's a very nice topic to talk about. If you're heavily involved with GPUs, I actually work for the Lumi team, so I work with the other CCL. A second remark, that's to the EasyBuild community. One of the reasons why I hate RPath is precisely the ABI story. We're confronted on Lumi, we're confronted daily with having to inject our optimized MPIG implementation for the Cray Slingshot network into containers or into applications like ANSYS. If you use RPath style linking instead of runpath or LD library path, you do not only have to think about what to inject, you also have to think about where to inject. So you make life even more complicated.
Yes, this is one of the driving purposes of the work done is exactly, whether it's taking binaries into Amazon for EFA or for Cray. And NERSC has all sorts of lovely problems with people's open MPI containers. And actually, so the reason I did the ABI is I worked in the HPC software product group. And my boss at the time said to me, I told him I was working on it. He goes, you should do this because every single one of our distributed math library projects and more has this problem, right? We ship NVIDIA'25. It has an MPI ABI abstraction. We ship CUPy numeric sitting on top of Realm, which also has this problem. All of our math libraries use NVIDIA'25, not MPI. One, because they're crazy and they're smart and they can use it and it will lead to maximum performance, but also because that's the only way that they can safely not depend on an MPI ABI. So the amount of stuff, even for us, I was motivated strictly by our own proprietary software deliverables to solve just even bootstrap launching of MPI or distributed libraries that use MPI. So my hope is it takes off, we got everything right, and we all laugh about the days when this was a problem.
And you actually see with your friendly competitor who's not here anymore, that they actually lack distributed memory math libraries, equivalents of some libraries that exist in the CUDA ecosystem, probably precisely because they would compile for OpenMPI, but then you have systems that use MPIG. So you would need to recompile those libraries.
Look, I mean, all of our stuff, our product from Mellanox HPCX is OpenMPI based, and we have a whole bunch of really important customers that use Cray. And AWS buys, you can find out from the internet how many digits are in the amount of stuff that they buy from us. We want Nickel and NVIDIA' to run on AWS EFA. So we don't see any problem, right? We want to solve this problem. We want to support all the MPIs. And if other people benefit from that because it's the right thing to do, of course we're happy with that. It's fine.
Any other questions? You had a slide where you showed that the ABI depends on, I can't remember exactly, there were 3 things like operating system, something else, something else. Yeah, this one. So what does this exactly mean? Does this mean that I cannot take an MPI code from one operating system, but I mean operating system?
What do you mean by operating system?
Yeah, so
can you go from
different flavors of Linux?
Can you go from Linux 2.6 to Linux 4.2? I think so. I think the dependency is strictly glibc.
Right.
So the thing is, you can go forwards in time.
Yeah.
But Can you build on Ubuntu and go back to Red Hat 6? No, because Red Hat 6 sucks, right? I mean,
Okay.
the glibc is like so old, right? And people still use it. It's terrible. So there will always be a path that this will break, but it's a path that will break for everything because of glibc. So I said that vaguely because of AIX. Like on AIX, you can do Q32 and Q64 and change the size of a pointer. You can also do that on x86. Nobody does it. On 64-bit AIX, the default pointer size is 32. So you have to change it if you want to use more than 2 gigs of memory per process, right? So there's a whole bunch of stuff hidden behind there, but by and large for Linux, the answer is you have to have the right libc. So you're either on a glibc system or you're one of those people that insists on using Alpine and talking about it and then, using Musel.
Yeah, okay, clear, thanks.
Any other question? I have maybe a short one. I remember when I started working in HPC now about 15 years ago, there was a bit of buzz that MPI was going to die really soon. And was going to be replaced by PGAS and all these fancy things. That clearly hasn't happened. Are we now in a situation where we're pretty confident that MPI is here to stay for another 30 years? Or?
So the reason MPI didn't defeat PGAS is because they have been assimilated, right? So I gave a talk to in the greater Baltimore, Maryland area, which is of course the epicenter of non-MPI PGAS usage in the world. And I gave a talk to them about how MPI is a PGAS model. And I got Kathy Yellick and Bill Carlson, right? Kathy invented UPC, and Bill was part of the invention of both SHMEM and UPC. I got them both to admit that MPI is a one-sided model now. They didn't say that they liked it or that it was fast, and that's fine. I didn't need them to say that. But right, we captured the semantics of SHMEM and the requirements, by and large, of GasNet, the requirements of RMC, of co-array Fortran, into MPI. Because it's not, MPI is not a message passing standard as meaning the MPI-1 semantic. It just happened to be that name because in that era, that's what we did. But it really is the HPC distributed communication standard. And we will assimilate everything that makes sense, right? And that's good for everybody, right? Everybody wants it to be easy like MPI. So we'll assimilate all the stuff that is a standardizable, reasonable practice. And then MPI doesn't have to take anybody else's market share, right? Co-array Fortran thinks that they compete with MPI, in some ways. Some people are like, oh, co-arrays are better than MPI. And right, what they're saying is, I like to use co-arrays for my code more than I like to use send receive. But the joke's on them because most of the time they're using MPI. They just don't know it, and that's fine. I am happy that they're happy using co-arrays and not knowing that they're actually achieving their performance portability on most networks with the MPI standard, right? I don't use MPI in NWChem. I just want NWChem sitting on top of global arrays, sitting on top of RMC to be able to use MPI and work everywhere. So MPI is not going to die until we so thoroughly disrupt what it means to do parallel computing that we cannot capture the semantic into what MPI is. But we're doing a pretty good job. There's, fault tolerance, some of the dynamic execution is a little bit stressful, but we have stuff like sessions. I'm confident that we'll get there. But there are always disruptions. I would say the GPU stuff is the most difficult thing because it's a fundamental change in the execution model that the code runs in. So MPI has been basically the CSP communicating sequential processes, right? A C abstract machine thread executing. Now, many of these executing in parallel, talking with MPI. Well, that's not what GPUs do. They are not a C abstract. They're not a PDP-11. They're not an abstract machine like the ISO language standards think they are. And therefore, we have to work really hard to try to get MPI to grow out of that abstract machine model of what is a computer, what is a process, without making a whole bunch of non-portable assumptions, because it's not MPI if it only works on NVIDIA GPUs or if it only works on NVIDIA and AMD GPUs, right? We want to be portable, and we're willing to wait, right? We waited to do one-sided the way we did because we needed it to be portable, and we're going to wait to do GPUs, but we can hopefully get it right and it works everywhere that matters.
Yeah, to some extent it's similar to Fortran, yeah. And also that is getting a revival, right? With the whole... Yeah. Okay, I think we can wrap up here. Thanks a lot, Jeff. And by the way, Jeff is going to join us for the karting this afternoon as well, so you can race NVIDIA and see if you're faster than them.